Today, we're going to take forward our discussion on vibrations and oscillations inside crystal structures. We specifically focus a little bit on this idea of the Brillouin zone. So we've already seen monoatomic and diatomic lattices in one dimensions, and we've derived their dispersion relationships. So these dispersion relationships are a signature of energy versus momentum or frequency versus the wave number. So if we focus on 1D monoatomic lattice which has one atom per basis, the dispersion relationship looks like the following. So here is our omega, here is our k. And why do I call this the energy? Because if I multiply this omega with h bar, I will get dimensions of energy. If I multiply this k with h bar, I'll get dimensions of momentum. So this is an energy axis, whereas this is a momentum axis. Momentum has both speed of a wave as well as its direction. For 1D, there is only one direction possible, in fact two, left or to the right. So for a monoatomic lattice with one atom in the basis, some spring constant k shows the interaction between these atoms, and if the spacing between two lattice points is a, then the relationship that we obtained was a sine square curve which extends in both directions, is periodic. So it starts off at 0, it goes to some maximum value which is proportional to k over m square root. This point is, if my k or q, I had used q in the previous lecture, so let's stick to k from this point onwards. So if this k is pi over a, and this k here is minus pi over a. And I mentioned that this spacing between these two maxima in the k space is 2 pi over a, which is simply the length of the reciprocal lattice vector. And since this is periodic, do keep in mind that if I take, for example, this lobe and I translate this lobe by minus 2 pi over a, or minus the length of the translation vector, I get to this point, to this lobe. So this lobe is repetitive with 2 pi. So I can fold back all of this back into the region in between these dashed lines. So the regions outside this Brillouin zone, which is called the first Brillouin zone, can be folded back into the first Brillouin zone by translations through reciprocal lattice vectors or multiples thereof. So this is the situation for the monoatomic lattice. The dispersion relationship, of course, is proportional to sine square qa over 2 or ka over 2, and so on. And then we shifted our attention to the two-dimensional 2D, 1D diatomic lattice. And so on. So now let's suppose the periodicity is d. The spacing between two neighboring atoms is still a, but the periodicity is now d, which is double the length of a. Now in this case, since if we plot the dispersion relationship, we have again a periodic structure. Now D is twice of A. So which means that if I were to use the same scale for this K axis between these two graphs, I will again get periodicity, but now the period is 2 pi over D. So this is pi over D, which is pi over 2A, and this is minus pi over D, which is equal to minus pi over 2A, since D is twice the length of A. So I get a periodic structure, a periodic dispersion relationship, and I get this branch here called the acoustic branch, and I got a branch here. So we do notice now that this region, this periodic region, this complete one period is now shrunk with respect to the 1D case. So the Brillouin zone has shrunk. It has shrunk because the lattice spacing has doubled. The length of the reciprocal lattice vector is now 2 pi over D instead of 2 pi over A. So the entire Brillouin zone has shrunk. And of course this is a periodic function, so this repeats itself. Okay, so the one thing that we observe is that the Brillouin zone has shrunk, and we also see this translational property is that this entire second period can be folded back into the first period by a translation through the reciprocal lattice vector. So everything is periodic in the reciprocal lattice vector. So if I somehow, so this is now an example between a monoatomic and diatomic lattice. These kinds of expansions can also take place in 3 dimensions. For example, the size of the unit cell can double. If the size of the unit cell doubles, the first Brillouin zone shrinks. This doubling can happen with the result of temperature. It can mark a phase transition. We also observe that in this monoatomic case, there is no optical branch, whereas in this diatomic case, there is indeed an optical branch. Okay. So if I were to now change this situation such that the mass of this atom is different from the mass of the other atom inside the basis, but if the masses get equal, I get a transition from this dispersion relationship to this dispersion relationship. Correct? So all of this is looking really neat so far. And how do I know that? So if I were to take this branch, I could take this branch, and this branch is totally equivalent to this section of the branch. This section of the branch is just the same as this section of the branch because they are only related by translations inside the reciprocal space. One thing I would just like to mention is If I were to take the 1D monoatomic case, let me plot it again, right? This is the first Brillouin zone, half of the first Brillouin zone. So this is 0, this is pi over A. Okay, this is half of the first Brillouin zone, the region that I have over here. So I've just zoomed in onto this region and plotted it here. Now if somehow if I were to have a 2D lattice, if I plot the 2D dispersion relationship superimposed onto this, I draw this hypothetical line, okay, and then I notice that what I really have is, if my D is double, this is pi over 2A The dispersion relationship, this is pi over 2A, this is pi over A, so probably what I've done, pi over 2A. So this, I've actually dilated this figure a bit too much, so it's not to the same scale. So this white is my dispersion relationship for the monoatomic case. Monoatomic, 1D. And for a diatomic case, I know that my Brillouin zone has shrunk. So the zone boundary now, instead of being pi over A, is pi over 2A. So if I look at the dispersion relationship for the diatomic case, which I now plot in yellow, what do I get? I get this curve here, followed by this curve here. Okay, so a gap appears here. Okay, so let me now draw the two graphs to the same scale. So this is my monoatomic case, this is pi over A. It goes like this, right? There. Okay, this is the monoatomic case. This is minus pi over A. Now let's draw the diatomic case. For the diatomic case, the Brillouin zone has shrunk, minus pi over 2A, and it's drawn like this. So this is it. Here you go. And then there is this optical branch here. So this is the diatomic dispersion relationship as we saw in the other class. Now, why is this true? Because if I extend this, it's periodic, so this goes like this, here. Yes, this goes like this, and so on. So this is now the yellow diagram and the white diagram, when drawn over all values of K, is called the extended zone scheme. So I've drawn the dispersion relationship for the diatomic case in yellow, and the dispersion relationship for the monatomic case in white. So now what you observe is that this is the period, this much is the period for the diatomic case. All right. So this white curve for the monatomic case has split asunder. It has shown a fissure at this point, at this zone boundary for the diatomic case. So this white curve has now been split when the two masses are different, or the two objects have different chemical identities. So a gap has appeared inside this dispersion relationship. It's a kind of a band diagram, and this gap is a kind of a band gap for mechanical waves. Okay? So whenever we have introduced this additional moiety in the two diatomic case, the additional kind of atom, a gap has appeared in the dispersion relationship. Okay? And you can immediately tell that this is true because this curve, this part of the branch, of the optical branch, you will notice that this is the same as this part. So if I shift this part by minus 2 pi over 2a, because 2a is now the period, or if I shift this by 2 pi over 2a or pi over a, this part is entirely shifted here. So it's evident that this white curve has split into, it is showing a discontinuity at the boundaries of the Brillouin zone. So it's showing a discontinuity here, and it's showing a discontinuity here. This discontinuity will be bigger if the two masses are vividly different. If the two masses are totally different, the discontinuity is going to be larger, right? So this discontinuity in the energy or in the frequency that appears at the zone boundary. So there is a discontinuity over here, and this discontinuity at the zone boundary refers to a band gap. Now if you introduce a wave inside this crystal, since it's a one-dimensional crystal that we're talking about, any wave and there's only one kind of wave that can be transmitted, which is longitudinal. Okay, the amplitudes have to be parallel to the 1D lattice because it's a 1D lattice. So if you look at the gap, you cannot transmit a frequency that happens to fall inside this gap. Such a wave cannot be transmitted. Okay, so it will be wholly and solely absorbed. So this crystal can now act like a mechanical filter. Okay, any questions? So now we do also know that there is this kind of diagram that we can draw for the dispersion relationship. This diagram, which shows all the Brillouin zones, is called an extended zone scheme. If I only show the first Brillouin zone, so if for the same dispersion relationship, if I just plot for the two diatomic case pi over d and minus pi over d, if I were to just plot inside the first Brillouin zone, it's called the reduced zone scheme. And it's sufficient to just mention or draw only the reduced zone scheme, because everything else can be folded back into the reduced zone scheme. So all the drama takes place inside this first Brillouin zone. Okay, so this expanse is the first Brillouin zone. Okay. Now one more thing I would just like to mention is that of quantization. Now let me draw for the diatomic case. Everything is now in 1 dimensions, but it can be extended to 3 dimensions as well. So this is my K. I have pi over D, okay, minus pi over D. This length is 2 pi over D, which is the length of the reciprocal lattice vector, and I have a dispersion relationship, of course, an acoustic and an optical branch. 2 branches. 2 branches because it's diatomic, and I'll formalize this in a minute. All right, now from the graph it looks that all K values are possible inside this regime. And for one K value, we have 2 omega values, omega 1 and omega 2 for the same K value. Okay? And there is a continuum of K values. However, whenever you have an object of finite length or a 3D crystal of finite size, a macroscopic crystal of finite size, it has surfaces, it has edges. So the number of atoms n and the number of lattice points n is finite, it is fixed. So in these cases, this confinement leads to quantization of the K values, which is a general tenet of quantum mechanics as well. So you do not have a continuum of K values, rather you have just a finite discretization of K values possible. And the spacing between 2 K values can also be determined from simple principles. So this branch really is a collection of, it could be a very large number, no doubt a very large number of points. So this branch could be a collection of finely spaced K points. Now I have super exaggerated the spacing between these points, but these could be millions of points, and we'll kind of have a qualitative argument of how many in a second. Likewise, the optical branch could be a continuum of K points. And it has to be finite because the degrees of freedom is finite. Suppose there are n atoms and a monoatomic lattice. N atoms, monoatomic lattice, there's only 1 degree of freedom per atom. It can move along the x-axis. Only 1 degree of freedom. So there are n degrees of freedom. So if you write down the equation of motion, there cannot be more than n solutions. So there should be n solutions. So this acoustic branch, which only exists, which is the only branch that exists for monatomic, can only have n points, where n is the number of atoms. So the size dictates the quantization. How many points exist inside a branch? For a diatomic case, you have 2 kinds of atoms, so there are 2n branches. There are 2 branches and 2n modes or 2n degrees of freedom. Okay, each degree of freedom is also called a mode in the language of quantum mechanics. So each degree of freedom is also called a mode. So if you have n atoms and r atoms per basis, you will have r into n modes. Okay, for the 1-dimensional case. But if you have a 3-dimensional case, you will have 3rn modes. So this is the number of modes that exist, which is also equal to the number of K points that exist, and it's finite. So everything has to be digitized. Okay, and the number of modes that exist and the number of branches that exist is 3 R. So this is the number of branches that can exist. Monoatomic, there are, now we're talking about 3D. Monoatomic, in 3 dimensions, there will be 3 branches. Monoatomic 1D, there will be 1 into R, 1 branch. So you really have XR branches, where X is the dimensionality of the system in space. 1D, 2D, 3D, etc. So there will be 3 R branches for the 3D case. Okay, if for the monoatomic system. So if I take a cubic lattice, simple cubic lattice, and there is only one atom in the basis. One atom in the basis, which these atoms I'm showing by in this pink color. There will be 3 into 1, 3 branches. And all 3 of those branches will be of the acoustic kind. Because when you have a wave, there could be a longitudinal wave, and in 3D you can also have 2 kinds of transverse waves. You can have an oscillation like this, oscillation like this. So there will be 3 acoustic branches, and if I were to plot them in 3D, so this is my Q or K. In the first Brillouin zone. Now in 3D, when you plot dispersion relationships, you also have to mention which direction is K, and the dispersion relation can be different in different directions. For cubic, it's very simple. But for simple cubic, it's simple for the first Brillouin zone, but not so for the higher order Brillouin zones or for phase center. And we'll look at examples of this kind when we move to the laptop. So suppose I look at the dispersion relationship plotted along Kx. So there will be 3 branches, 3 kinds of acoustic branches, because there are 3 into 1, 3 branches in total, and all 3 will be of the acoustic kind. So there will be 3 branches. You could also have, so one of these branches will be corresponding to the longitudinal acoustic branch, let's call it LA, and the other 2 will correspond to transverse acoustic branches, TA1 and TA2. It's also possible that you have a longitudinal branch and the 2 transverse branches, they kind of superimpose on one another. They have the same dispersion relationship. So they are degenerate. So along high symmetry direction, it's very likely that there is no distinction between the 2 transverse acoustic branches. So it appears in a dispersion relationship, it appears that there are 2 branches, but in fact there are 3, because 2 of them are degenerate. So there will be, and if there are more atoms, so in the diatomic case, there will be 3 into 2, 6 branches, right? There will be 6 branches. So 3 of them will be acoustic, which have a property that at K or Q equals 0, the omega is also 0. And here they are almost linear. So there will be 6 branches for the diatomic 3-dimensional crystal. Diatomic means 2 atoms in a basis. So 3 of them will be acoustic and the other 3 will be optical branches. So here is for my K along a particular direction. This is my first Brillouin zone, which I abbreviate as first Brillouin zone. 3 acoustic branches, and 3 optical branches, perhaps like this, right? So there will be a longitudinal optical, transverse optical 1, transverse optical 2, and so on. And again, you can have degeneracy in the optical branches as well. But there will be 6 branches. Some of them can be degenerate for a 3-dimensional crystal which has 2 atoms in the basis. Now coming back to this idea of quantization, how can we find out, we now know the total number of modes or the total number of points that can exist inside the first Brillouin zone. And it's sufficient to just mention the first Brillouin zone because everything is then repetitive. Now if I look at my quantization problem, let's come back to the 1D case. So if I have a 1-dimensional chain, so I'm not drawing the springs because that is kind of symbolism anyway. So if I take this chain which has n atoms, n is supposedly very large, and if I can find out the quantization by wrapping this chain of spins on a ring, right? So this chain is now forming a ring, and if my displacements are such that the displacement for the first and the nth, so it's periodic, so the boundary conditions are periodic, which means at the boundaries, so at one edge what happens is the same thing that happens at the other edge. So the amplitudes of the waves are equal at the 2 edges because we have tied the ring in the string into a ring. So if you apply these periodic boundary conditions, we do know that if I have an atom in the nth unit cell, I have a phase which is EIQ NA, right? I know that there is a phase associated with the nth lattice point which is EIQ dot Rn. Okay, because if you remember, we kind of came up with this amplitude S equals U for monoatomic EIQ dotted with Rn. Right? In 1D, this becomes U EIQRN, right? You do remember that. And this is U EIQ, Rn is nth NA, where n is the running variable. So one point is, so here we have n equals 0, and when we wrap it around, we get back to n. So the amplitude, this phase, at n equals 0 must be the same as at n equals capital N. So this means that if I have EIQNA, this must be equal to EIQ0, which must be equal to 1. Let's choose K now, right? Okay. So this means that KNA is some multiple of 2 pi. Let's call this P, some multiple of 2 pi. This means that K is 2 pi over A, which is really the length of the reciprocal lattice vector, 2 pi over A, sum P, which is an integer, and 1 over n. Okay, so this K is now indexed by this integer P. Okay, and P goes from 0 in the first Brillouin zone. This P goes between 2 edges, right? So there is this diagram here. In the first Brillouin zone, it can go between two kinds of values. Remember that my capital N is large, so P is some integer between minus n by 2 and n by 2. And the total number of P's that exist inside the system is n. N by 2 on one side of the 0 of the reciprocal, that is, and n by 2 on the other side. So this k is now quantized. And what is the spacing between two successive points is 2 pi over n into a. So the spacing between two successive points, delta k, which is this spacing here, right, is 2 pi over na, correct? What is n into a? Total number of points and the spacing between two atoms. What does it give us? The total length of this solid in 1D. So this is 2 pi over L. So the spacing between these points is 2 pi over L. So if you look at this spacing and you multiply it with the total number of points, so if I take this spacing and multiply it with the total number of points, which is n, if I total number of points, what should I get? So I will get 2 pi over a, which is the length of the first Brillouin zone, which is the size of the first Brillouin zone. Okay, so the k values are quantized. The number of modes inside the first Brillouin zone is 3 times the number of atoms in the basis times the total number of atoms. In 3D, the spacing between two k values will be the three-dimensional analog of this, because now you will have to impose this periodic boundary conditions, which are also called the von Karman boundary conditions. You have to impose them in 3D. So kx will be quantized, ky will be quantized, and kz will be quantized. So this entire three-dimensional reciprocal lattice is quantized in its k values. The spacings can be very small, okay, because the size of the crystal can be very large. Now let me also now look at the Brillouin zone in a bit more detail and try to kind of invoke what is really happening here. So if in 1D, it's all very simple. So this is my direct lattice. The crystal structure has been made by adding atoms to the lattice. So this is E. And I know that my first Brillouin zone extends from minus pi over A to plus pi over A. So the reciprocal, this is my reciprocal lattice vector, right, pointing in this direction, which has a length 2 pi over A. All right, and my Brillouin zone extends from minus pi over A to plus pi over A. So now if I were to draw the reciprocal lattice superimposed on the direct lattice, this white is the direct lattice. Okay, so now if I draw my reciprocal lattice point, the k values that exist. So the first Brillouin zone extends from between 2 points. One is at plus pi by A and the other is at minus pi by A. So this region, so now this is the k space. This region here is the first Brillouin zone, and the 0 of this first Brillouin zone is in the exact middle. The next reciprocal lattice point is here, isn't it? So if this is my any lattice point inside the reciprocal, which I take as the origin. This is the next reciprocal lattice point, and this distance is this length, 2 pi over a. And in the reduced zone scheme, this is my first Brillouin zone. After that, I will have the second Brillouin zone, the third Brillouin zone, and so on. So after this, this is my second Brillouin zone here. In fact, the second Brillouin zone can be drawn here. In fact, it's slightly more complicated. The second Brillouin zone is this much. This one. Because this is equivalent to this. This is my second Brillouin zone. And then third Brillouin zone, and so on. Now, if you look at this, let's focus our attention on the first Brillouin zone. This is my k-axis. The reciprocal space is this entire line. Now, which points qualify to be in the first Brillouin zone? I take a particular lattice point as my origin. So this point here is closer to this lattice point than any other lattice point. So there's a lattice point here, and so on. So the points in this entire region are closer to this point than to any other lattice point. Correct? So this locus of points in the reciprocal space which are closer to a particular point, to the origin of the reciprocal lattice, forms the first Brillouin zone. Okay? So this kind of unit cell inside the reciprocal lattice, which comprises all the region around the origin of the reciprocal point, such that all the points in the region in that region are closer to that origin than any other point. Such a unit cell in the reciprocal lattice is called the Wigner-Seitz cell. Wigner-Seitz cell. So the first Brillouin zone is the Wigner-Seitz cell in the reciprocal space. Now it's really convenient to look at this in a 2D example. So if I draw a square two-dimensional reciprocal lattice, which is the Fourier transform of a two-dimensional direct square lattice. Square is easy. So suppose this is my origin. I want to draw the first Brillouin zone about this origin. So what I do is I need to find the region inside this reciprocal lattice which is closest to this point than any other point. Okay, it will be, so how do I make that? So I draw the reciprocal lattice vectors emanating from this point, and I draw these reciprocal lattice vectors to the points that have the smallest distance to this point and are equidistant to it. So all these 4 points have the smallest distance. So these are the minimum sized reciprocal lattice vectors inside this crystal. Now what I do next is I draw bisectors of these reciprocal lattice vectors of minimum length. So there's a bisector here. Now I draw this in faint lines. I bisect this, I bisect this, I bisect this, and I bisect this. So this region here, which is inside these bisectors, is the Wigner-Seitz cell in the reciprocal lattice, and this qualifies for the first Brillouin zone. So this is the first Brillouin zone. And the k values inside this Brillouin zone, they will all be quantized. Okay, so there will be a large collection of points here inside this Brillouin zone, and you can count the number of these modes. It depends upon whether it's how many atoms are inside the basis and how big is this crystal, 2D crystal. And the spacing in each dimension is 2 pi over Lx, where Lx is the length along the x direction, and 2 pi over Ly along the ky. So this is my ky direction, this could be my kx direction. Okay, so I know the spacing along each dimension. And this is the first Brillouin zone, which is formed by the region inside these. These are in fact planes. Okay, these are planes, and I'll show in a minute that these are called the Bragg planes. So these are all planes. Here is a plane, here's a plane. So the region which is inscribed, which is circumscribed by these planes, the region in the interior of these planes is called the first Brillouin zone. And then if I want to find the second Brillouin zone, I take this origin and look at the lattice points that are around it with a length bigger than these reciprocal lattice vectors. So here is one point here, another point here, another point here, and another point here. Okay, so these are next in line in terms of distance from this origin. So I draw lattice vectors, translational lattice vectors to these next in line points. And then I draw bisectors to this line. So now this region is already the first Brillouin zone, this region. Let me thicken this plot here a little bit. So this is the first Brillouin zone which has lots of k points. Okay, k points are actually corresponding to crystal oscillations, a wave, a sound wave, or an optical wave, or an oscillation that is happening inside this crystal, right? Now if I look at the regions that have now been created, which are outside the first Brillouin zone and are circumscribed by these new planes that have been created. So this region here, this region here, this region here, this region here, right? These form the second Brillouin zone. Okay, and it's nice to see that if I take this, now the second Brillouin zone is kind of punctured. It's discontinuous, it looks like discontinuous. It's not mutually connected, but it's in bits and pieces. But if I take this point, this second Brillouin zone, and I translate, so what is the length of the reciprocal lattice vector? This much is 2 pi over a. This is the length of the reciprocal lattice vector between two lattice points, right? This thing, this is which is the distance between this and this. So these are 2 points. These are 2 reciprocal lattice points, right? So this distance is the same as this distance because this is a perpendicular bisector. So this is the length of the reciprocal lattice vector, and this is the length of the reciprocal lattice vector in the other dimension. So if I take this point and translate this by this length, this object will be transferred here. So this 2a region goes here, 2a. This region, 2b region, this thing goes here. So everything can be folded back into the first Brillouin zone. Correct? So this is the periodic property for the Brillouin. And likewise, I can construct higher order Brillouin zones, and it gets a bit more complicated. But I can do that, and I have a diagram to show that. And remember that the size or the area or the volume of the first Brillouin zone is the same as the second Brillouin zone. So there are many smaller pieces, but many of them, and overall they combine to give the same overall area. Now a note about these planes that are at the boundaries of the zones, and they're very important. We've already seen that for the diatomic case, or when you have many atoms inside the basis, there are gaps that appear at these boundaries. There's a discontinuity. Okay, and this discontinuity has important implications as well. And whenever there is a gap, notice that if you look here, this curve kind of slopes downwards a little bit. So the derivative of this curve, we'll notice. So this is omega, this is k. The derivative of this curve is d omega over dk, which is called the group velocity. So the derivative of this curve, in fact the inverse of the derivative of this curve is related to the effective mass and other concepts. Right now we're looking at crystal oscillations inside the solid. The same ideas of the Brillouins are also applied to electrons inside the solid, which will be our next line of attention. Okay. So now we know the Brillouins. And one last thing I would like to talk a little bit about is these planes that are formed at the edges of the zone. These planes are called Bragg planes. And they are related to diffraction, in fact. So if I look at my Bragg reflection, which is a model for X-ray scattering. So there's a plane, a reflecting plane, an incident X-ray comes in and is reflected in the Bragg model. So this unit vector S naught, it's a unit vector for the incident and S for the reflected, and we've used this notation before. Okay, so if I look at how much does the, I also know that my k is 2 pi over lambda s, right? This is a unit vector, but k is this, and my k naught, my incident wave vector is 2 pi over lambda s naught. So the wavelength of the incident and the reflected X-ray is the same. It's like an elastic process. No change in energy. So if I kind of extend this vector here, this is my S naught, then this vector here is S minus S naught, correct? I know that this angle is 2 theta, the angle of deviation is 2 theta. So this is 2 theta, so this is theta, this is theta. So the k, delta k, and don't confuse this delta k with the spacing there. This is the change in the wavelength, the change in the momentum, or which is only due to the change in the direction of the X-rays, is 2 pi over lambda S minus S naught. And by the way, we know from the evolved construction and from the Bragg reflection that this change in delta, change in k, the change must be equal to the reciprocal lattice vector. We already know that, okay? And we can derive the Bragg reflection law from this. 2 pi over d and 2 pi over lambda. Let's see what S minus S naught is the length of this vector, right? And these are unit vectors. So this distance is, this length is 1, so this is 2 sine theta. This is sine theta, this is sine theta, because this length is 1. So this is 2 sine theta. So I will get 4 pi over lambda sine theta, right? So this is my delta k. right? So my delta k is, which is k minus k naught, is 4 pi over lambda sine theta, and I can put this equal to 2 pi over d. I will get 2d sine theta is equal to lambda, which is the Bragg reflection law. So this is making sense so far. So now if I look at k minus k naught, which is equal to this, must equal g. So if I look at this relationship, k minus k naught equals g. So let's rearrange, k equals k naught plus g. Now here we're talking about x is and diffraction, by the way, okay? So this is the Bragg reflection condition. So if I take the square of both sides, or take the dot product of both sides with itself, so this becomes k square, this becomes k naught square plus g square, right, plus 2 k naught dotted with g. Okay, so this k square is the same. So this means that my k naught or into g is half g square, correct, with minus sign. Correct. So this means that my k naught g equals minus half g dotted with g, correct? Now I divide both sides by 2. So it means k naught dot product with g over 2 minus half g dot with half g. Correct. Now I can replace g with minus g as well. It doesn't matter. So if I put minus here, this minus will become positive. It doesn't matter. So so if I replace g with minus g, this will become minus g, this will still be minus, and I'll get a minus sign here. So I can have this minus or positive, it doesn't really matter. Okay, now look at this expression and let's look at it diagrammatically. So I have some k naught. I'm kind of twisting this diagram a little bit. So I'm plotting it I'm twisting this diagram and plotting it again. So this is some k naught and this is some k. This is k minus k naught, isn't it? Which is g. This is a translation vector in the reciprocal space. Got it? Yeah. Now if you notice that, if you look at this expression, what is half of g? Half of g is this much, just up till here, half of this. Okay. So now if I take the dot product of k with half of g, which is I will get something along this direction. Okay. So what this expression means geometrically is that the dot product of k naught with g over 2 is going to be the dot product of half of g with itself, and this is a geometrical representation of this expression over here. isn't it? K naught dot product with G over 2, I will get some vector, some magnitude, some length here. So this is this length G naught over 2, isn't it? So K naught is a projection of K naught in this direction, and this is G naught over 2. And this is half of the reciprocal lattice vector. Okay? So this projection is equal to the dot product of half of G with itself. And this is the diagram that explains this in this expression. So half of G with itself. So half of G is this much. Take the dot product of this with itself is the same as the dot product of K naught with this vector. Okay? So this diagram explains this. Now if you look at this expression, it means that the incident X-ray and the reflected X-ray must be in this direction and in this amplitude. It's a constraint on the direction and the amplitude of the incident and the scattered X-rays. So you could alternatively have K naught here, but then K will be like this. You could have K naught here, but then K will be like this. So if this is the length and direction of K naught, this has to be the length and direction of K, which means that their tips, the head of one and the tail of one, must meet at the perpendicular bisector of the reciprocal lattice vector. And this forms a plane, isn't it? This plane is the same as the planes that I formed at the boundaries of the first Brillouin zone. So the boundaries of the first Brillouin zone are nothing but the Bragg planes. And so this is the connection between the diffraction and the first Brillouin zone concept as well. All of these X-ray, incident and scattered wave vectors or momentums must be in this precise directionality constraint and must satisfy the precise magnitude constraint. For example, you cannot have a diffraction and this is my K naught and this is my K, because then these vectors do not meet at the Bragg plane. Okay. Now these Bragg planes are really important, as we will see. They form the edges of the first Brillouin zone, and so from this book I've taken this diagram. This diagram shows a square lattice and its reciprocal space, and it shows the first, second, third and fourth Brillouin zones. It's an iterative process of making these Brillouin zones to higher order. In each case, if you take the sum of all the 2 regions, sum of all the 3 regions, all the 4 regions, it will give the same volume. Okay, so this is how these higher order Brillouin zones can be constructed. Now when you look at the simple cubic lattice, its reciprocal space is also simple cubic, primitive cubic, we know that. So the first Brillouin zone in this case will be this dashed cube, which is shown in dashed lines. That's the first Brillouin zone. Very nice, very simple. And the length of the Brillouin zone will be 2 pi over a on each side. The second Brillouin zone will be these slanting, so this is a square, another square, another square. It will be these kind of slanted squares. Okay, and their faces will be perpendicular to the 110 family of directions. So this is the second Brillouin zone outside the first Brillouin zone. If you have the body-centered direct lattice, we know that its reciprocal space is face-centered. So for this face-centered reciprocal space, which is the Fourier transform of the body-centered lattice, and then you draw the first Brillouin zone, it comes out to have these this shape. It will have many faces, multiple faces, probably 10 faces. Likewise, for a face-centered cubic, if you were to draw the primitive rhombohedral cell that is formed inside this face-centered cubic lattice, and then you take the Fourier transform, you get a body-centered reciprocal space. Now, for that body-centered reciprocal space, if you were to draw the first Brillouin zone, it will have this complicated shape. It's bounded by these polygons. There are hexagons, there are squares. Okay, so this is the first Brillouin zone. Now, how do we identify directions inside this first Brillouin zone? Because we have to plot dispersion relationships. Dispersion relationships are omega versus k. Now, there's kx, ky, kz. But so you have to plot along multiple k's to get the full picture of the dispersion relationship. All k directions are not the same. So when you make these plots, and I'll show you how to make these plots, but let's first of all consider some dispersion relationships for cubic systems. Lead, for example, is cubic and it's monoatomic. The basis contains just lead because there's only lead. So it must have 3 branches, acoustic, and all of them will be acoustic. So there is one longitudinal branch and 2 transverse branches which are kind of superimposed onto one another. Along a different direction, along this 1, 0, 0 direction, this is along the body diagonal, this is along the edge, the dispersion relationship changes. So it slopes down a little bit, but still the transverse acoustic branches, they are degenerate. In sodium, along the edge, sodium we know is face-centered cubic. So for face-centered cubic, it has a complicated Brillouin zone, so you have to specify which direction you're talking about. This, by the way, is a normalized k-axis. So this is 2 pi over a, which is divided by the maximum. So this has been normalized. So again, there are two degenerate transverse acoustic branches and 1 longitudinal. For another dimension, which is along the diagonal of a face. Now these are directions, by the way, in the reciprocal space that are being shown here, not the direction in the direct space. So along kx plus ky direction in the reciprocal space, the degeneracy is lifted between the 2 transverse acoustic branches. So you get these 3 branches in full glory. Likewise for silicon. Now silicon has a face-centered cubic structure, but now like diamond, its basis has 2 atoms. Okay, its basis now has 2 atoms. So there will be 6 branches. 3 of them have to be acoustic and the remainder 3 are optical. And the 2 transverse acoustic branches, they are degenerate. And if you look at the optical branches at k equals 0, they start off with some omega and slope downwards. And all 3 optical branches start off at the same point, and then they spread out. And the transverse branches, acoustic and optical, have wide spacing, but they start off at the same point because the 2 kinds of atoms, both of them are neutral. So this is a covalent solid. It's a covalently bonded solid. However, if you look at another cubic structure, which is face-centered cubic as well, potassium bromide, and look at the dispersion relationship along the body diagonal, still it will have 6 branches. Okay, exactly the same thing. The spacing between the transverse branches is now not very big at the edge of the Brillouin zone, at the zone boundary. But the longitudinal and the transverse optical branches, they have different omegas at K equals 0. Now this is an ionic crystal. Potassium is a cation, bromide is an anion. So it can absorb electromagnetic radiation like optical radiation in the terahertz regime or the infrared regime. So it can absorb infrared radiation. That's why it shows up in an infrared spectroscopy experiment. So this gap at K equals 0 between the optical transverse and longitudinal branches is representative of an ionic crystal in many cases. So the dispersion relationship tells us the whole story of how these lattice vibrations are occurring inside the solid. Now you can identify different kinds of directions. For example, the center of the K space is always called the lambda point. And you move along Kx or Ky, when it touches a zone boundary, it's generally called an X point. Then at the half of the edges of the Brillouin zone, there's an M point. And then in between, you have the sigma and the Z points. You also have this lambda point. So this is how the nomenclature is kind of unfolds for different kinds of reciprocal lattices. This is the first Brillouin zone of phase center direct, first Brillouin zone for a HCP, hexagonal closed pact, which is also phase centered cubic for BCC and so on. So these kinds of special points exist. K, W, U, X, L, and so on. And then you plot the dispersion relationship along a line. For example, you go from this gamma point to X, from X to W, from W to K back to lab, to gamma. And you find out how the dispersion relationship changes along that direction. Because K vector is a vector. You have to see which direction you're looking at. And these dispersion relationships are found by Brillouin light scattering or neutron scattering or Raman scattering. The last slide is to give you an example of this. I've taken this spectrum from this paper, and it shows crystalline silicon. So notice here that this is the lambda point, this is the X point, W and K. So we are really going from lambda X W K. Lambda X W K is going from lambda to X, then along this square to W, then K. So we find a dispersion relationship along this trajectory here, then here, and then from W to K. So these are the acoustic branches, the optical branches, and the kind of crisscross, and again they're all degenerate, the optical branches are all degenerate at the center, and so on. So this is what a dispersion relationship looks like for lattice dynamics. In the next lecture, we'll see that we can quantize all of this. These lattice oscillations can all be quantized. They can be represented by quasi-particles called phonons. And phonons can be derived in the second quantization formalism. When these phonons exist, all of the calculations become easier. For example, you can find out thermal properties, elastic properties using phonons. So in the next lecture, we'll shift gears and move to a quantized version of this, which uses the description of phonons. Thank you very much.